Okay, so let me go ahead. Thank you for being patient with the delay on this month's ECSS Symposium. It's my pleasure to introduce Luke Wilson at TAC. Luke's been a long-time ECSSer. His work was also featured in the, I think it's like a PhD symposium at the most recent supercomputing, Luke?
That's right.
Yep, great. So Luke's been working with PI Daniel Bodoni from UIUC for several years now, optimizing a Fortran 90 code of his, and he's going to tell us a little bit about that work porting to the Xeon Phis on Stampede. So Luke, why don't you go ahead and take it away, and if folks on the call who are not speaking could mute, that would be great, because I don't have the type of controls I normally have to filter out background noise.
Nancy, before we go, did you send Luke's slide out yet?
Yeah, I'm going to in about 60 seconds. I'm waiting for Suresh's slide, and then I'll send it all in one note.
Okay.
Okay, so those of you who can't see the screen will have slides in about a minute or two. Okay, thanks. Go ahead, please, Luke.
All right, great. So, like Nancy said, for those that don't know me, I'm Luke Wilson. I'm a member of the High Performance Computing Group at TAC, and I've been working on this particular project in one form or another for the last 4 years. It's one of these continuously renewed ECSS projects. And I'm going to talk about things that have happened over the last 4 years to improve the performance of this Plascom CM code. So just a bit of an outline. I'm going to talk about the code itself in 1 or 2 slides, and then talk about the various things that have been done both to improve sequential performance and parallel performance, and then how we've translated that to the Knight's Corner Xeon Phi and our hopes for the Knight's Landing Xeon Phi to come. And so Plascom CM is a Fortran 90 code with MPI. It investigates the behavior of compressible viscous gases, and like Nancy said, the PI is Daniel Bodoni at University of Illinois Urbana-Champaign. This project is currently in its 4th year. The first 2 years were spent just restructuring. Hello? Okay.
We still got you, Luke. If everyone else could mute, that would be great. Thank you.
Okay. So the first 2 years were spent just restructuring the code to improve sequential performance and enable vectorization on the Sandy Bridge host processors that are in Stampede. And in project year 3, we changed the way that the domain is decomposed for MPI so that we can better use the smaller memory per core footprint on the Knight's Corner. And in the current year, we're preparing for a transition to Knight's Landing, but we're, of course, waiting for Knight's Landing to become available. So just a bit of background on the structure of the code. These are the 5 main functions that we've focused on over the last 4 years. Mostly focused on the compute interior derivatives and matrix vector multiply. As you can see down in the bottom corner there. These are the 2 routines that we've focused on extensively. The rest is not as large a contributor to the overall runtime of the code. So the first thing we looked at is the way that the matrices were encoded for the matrix vector multiplication. The original code used compressed sparse row for this stencil operation. In 2 dimensions, it's a 5-point stencil, which meant that using compressed sparse row, they were only able to get 5 contiguous memory accesses and 5 iterations per inner loop. So this translates basically if you could have a perfect vectorization done by the compiler, you get 1 4-wide double precision vector operation plus a scalar peel off that loop, which can be very slow. So we modified the code to use a custom diagonal representation. We tried the standard compressed diagonal, and found that since the nature of the code was so regular, we could do a more customized operation. This allowed us to increase the inner loop length from 5 to 40, and also gives us 40 contiguous memory accesses per inner loop iteration. So we have a perfect match there, which turns out to be exactly 10 4-wide double precision operations, or 5 complete level 1 cache lines per inner loop. And just changing the data encoding resulted in a 39% performance improvement, which is a success in and of itself. So this shows kind of the breakdown of performance for compressed sparse row versus diagonal. You can see compressed sparse row is the middle column there, and diagonal is on the right. Biggest thing here, percentage of peak went from 6.47% to 8.99. So this is our 39% performance improvement. And you can see that the memory accesses went down considerably. So we went from 1.15 loads per flop to 1.08, which may not seem a lot if you only do 5 or 6 flops, but if you have billions of flops, that can be an enormous amount of time saved not doing memory loads. So after we changed the matrix encoding from row to diagonal, we focused on getting the vectorization to all work properly. So the problem with the original code was that multiple compound types were used for the grid encoding. You can kind of see an example on the right. The problem was that the appearance of indirect access through compound type dereferencing prevents the compiler from being able to efficiently determine what is vectorizable and what is not. So we wanted to change all that. So we did a number of in-loop structure dereferences to alias out the compound type problem. And you can see here a change that we made on the right from the previous slide, where we've dereferenced using aliases all of these structure references. And this, combined with optimization flags for the Intel compiler, resulted in a 50% improvement in the code runtime on top of the 39% we got from the data structure re-encoding. So again, another positive result, and this led us to move on to actually implementing directive-based SIMD extensions, in this case using the Intel-specific compiler directives. So you can see here that once we added the SIMD directives to force SIMD vectorization, we gained another 30% improvement in the total runtime. So slowly stacking up performance improvements over and over and over again. We tried OpenMP for SIMD extensions, but we found that the Intel SIMD compiler directives were better, not by an enormous amount, but enough that it mattered. Of course, this was tried with Intel 14. We've not tried it with Intel 15 or 16, but that is something that probably be done in the works, especially in the future, especially moving on to Knight's Landing. So once we finished improving the performance of the sequential code, we decided it was time to finally tackle the problem of getting it to run on the mic. And the biggest problem with this was that the original code used a homogeneous domain decomposition to distribute all the MPI work, which is very simple and is very common for MPI codes. The problem is the memory footprint per task on Knight's Corner is very small compared to Sandy Bridge. At least in Stampede's configuration, we have 2 gigabytes per core on the Sandy Bridge primary host on Stampede. But if you want to use more than 4 tasks on the Knight's Corner, you don't get as much memory. The card itself has 8 gigabytes of memory total, so if you want to use 30 to 60 MPI tasks, for example, you need to have much smaller memory footprint per task. So what we did was change the decomposition strategy to be heterogeneous instead of homogeneous. And this allowed us to specify in the input parameters how many heavyweight MPI tasks we wanted. And these heavyweight MPI tasks would basically come out to 2 gigabytes per core for Stampede, although it's customizable. And then you can have some other number of lightweight MPI tasks for the cards. And we tried several different configurations for this, but and I'll show the results of that in a second. but this allows us to have many more MPI tasks running in a symmetric fashion on the card, and we wanted to keep this in symmetric rather than trying to switch the code to an offload form because we're preparing for Knight's Landing, and to the best of our knowledge, Knight's Landing will not have any offload capability in the way that Knight's Corner does. It'll be a standalone processor. It'll replace the primary processor in the host. So we wanted to keep this code in symmetric form rather than change it to offload. And here's a figure that describes the heterogeneous decomposition. You can see we've got this computational grid that has a 1D decomposition up at the top, and we've broken it down to use heavy tasks and lightweight MPI tasks. We send all the heavy tasks to the Sandy Bridge socket on the host, and we send all the lightweight tasks over to the mic. So relatively simple change that enabled us to do some interesting scaling results on the Xeon Phi cards. And you can see here this is a breakdown of trying different amounts of work on the Knight's Corner Xeon Phi cards. The vertical axis is speed up relative to using all 16 cores on the Sandy Bridge host, and the horizontal axis is the percentage of work that was sent to the card. You can ignore the percent sign, so 0.22% would be very small, but 0.22 here means 22%. You can see that in comparison to using all 16 cores, we actually get a 20% speed up, putting about a third of the domain on the Knight's Corner cards using 60 MPI tasks on the KNC. And although this seems like a lot of MPI tasks, there's almost no interprocess communication during each time step. It's only at the end of the time step that everything is resolved through MPI communication. So we were able to achieve a 20% speed up over using all of the cores in the Sandy Bridge host. And this is something we've seen fairly regularly with other codes as well, that we can get about 20 to 30% improvement over the entirety of the Sandy Bridge host, offloading about 30 to 33% of the work onto the card. You can see here, in this particular figure, we've got, again, vertical axis is speed up relative to 16 Sandy Bridge cores, and we're varying the number of MPI tasks this time, and each line represents a different amount of data that was offloaded to the card. In this case, the interesting one is the yellow line, which is 43% of the work transferred to the KNC. And you can see in this particular case, we can get almost 20% speed up, about a 15 to 16% speed up, using 48 tasks on the mic, which seems like a lot of MPI tasks, especially considering the small memory footprint per task you have. But for this particular code, it was decided that the easiest thing to do at first would be to try it without adding any kind of OpenMP threading to each MPI task. So this is a strictly MPI code still. Adding hybrid execution with OpenMP and MPI is something we're saving for a later time, and it's definitely going to be something that we're going to have to address as we move to Knight's Landing. So some of the problems we've had getting this to scale on the mic, but we have boundary conditions that are computed that are completely sequential at this point, and performance for sequential code on Knight's Corner is quite poor. The code actually has no capability to decide which parts of the domain have boundary conditions and which parts do not. So sometimes the boundary condition is solved on the Sandy Bridge, and sometimes the boundary condition is solved on the mic. So one possible solution to this would be to intelligently schedule boundary condition parts to the Sandy Bridge and then send the interior components to the KNC. Unfortunately, when we move to KNL, we don't have this option because there will be no fast host processor and slow accelerator processor, at least in terms of sequential performance. So the KNL will actually be the one and only processor going forward. So just to kind of summarize what we've done so far on the code, just the first 4 years of the project. So far, we've been able to improve the performance of PlasCom by a little more than 2.3 times, just by doing changes to data representation, switching from compressed parse row to compressed diagonal. This allowed us to change the inner loop structure to expose vectorization, reduce a lot of indirect memory accesses. It allowed us to have everything easily fit inside L1 cache and everything be cache line aligned, and then allowed us to include the SIMD directives that enabled all the vectorization and improved the performance so much. And then we also changed the domain decomposition from homogeneous to heterogeneous so that we could execute more tasks on the Knight's Corner card. And this allowed us to achieve an additional 20% speed up over the changes we were able to achieve in years 1 and 2. And when you added all this up, you get that 2.3 times number. And what this translates to, given the current allocation rates for this project, is a potential service unit savings of 12 to 14 million service units per year. So if they were running the exact same workload they would have run before any of this work had been done, they would need 12 to 14 million more service units every year to get the same amount of science completed. So we consider that a real win for this project, because our goal here is not only to just improve performance, but for performance sake, but to either enable more science to be done in the same number of service units, or to have service units available for more researchers to come to exceed and execute their codes. So, future plans moving to Knight's Landing. We talked about this a second ago with the roadblocks to scalability on Knight's Corner, but the boundary condition execution time for Corner is mostly cyclical. There's actually no deep inner loops involved in this particular algorithm. Unfortunately, KNC's sequential performance is quite poor, mainly because you have very slow 1 gigahertz cores. Each of these cores is very lightweight, so it's all in order execution. There's no branch prediction. There's no way to have the hardware perform any sort of instruction level parallelism to reorder instructions so that memory accesses that are causing halts are waiting in the queue while other instructions execute. So this makes performance of sequential algorithms on KNC very, very poor, but many of those particular roadblocks should be addressed by Knight's Landing. Of course, none of us have one yet, so we'll just have to kind of wait and see what Knight's Landing gives us. Of course, there will probably be more work to be done in terms of translating this particular code to hybrid using OpenMP, either through work sharing components or through OMP3 tasking to do some data level parallelism and expose parallelism for areas of the code that appear sequential but have a little bit of task parallelism that can be exploited. And that is my presentation, so if anyone has any questions, I'm welcome to answer them.
Luke, thank you very much, and apologies again for the delay getting started. Since we have a number of people on by the phone who can't use the chat feature, let me just open it up for a few minutes and see if there are questions from people on the call.
Hi, Luke. This is Sudhakar. So, how complicated or how much coding is needed? Recoding going from Knight's Corner to Knight's Landing?
So if we're so the question is how much recoding do we think is going to be needed to go from Knight's Corner to Knight's Landing? That's an interesting question because many of the I really don't know at this point. I mean, most of the work that we've done so far should translate quite easily to Knight's Landing, in terms of data structure reorientation and vectorization. In terms of hybridizing the code, it really depends on what kind of performance penalty we're going to take for the sequential sections. If we're not taking an enormous performance penalty for the sequential sections, a purely MPI code may still run relatively efficiently, and we don't have to do a lot of code changes. If the sequential sections of the code still underperform what we're seeing on Sandy Bridge or Ivy Bridge or Haswell, we'll probably have to dig into restructuring the code to exploit either more data parallelism or more task parallelism through OpenMP. So I really don't know how much work is going to be required there. I don't know if that's a non-answer to your question or not, but we're in a wait-and-see mode at this point.
Luke, so Knight's Landing is coming with the expansion of Stampede, is that right? And if so, what's the timeline that you're looking at for that?
Well, we have a scheduled upgrade to Stampede that should include some Knight's Landing, and I think we're looking at probably sometime in the summer or maybe early fall for that to be available and operational. Of course, we don't have any pre-production units or test units available yet, so we're really kind of at Intel's mercy on this one. But our hope is to have it sometime in the summer to be able to start this.
Yep. Okay. Great. We'll definitely keep ECSSers posted about when they can get their hands on such things too, since I'm sure everyone's excited. Other questions from folks on the call? I had just one question about what the working relationship was like with the PI group over such a long period. It sounds like you were able to get really quite in-depth with your code changes. I wonder if you could say a little bit about how that worked out in practice.
Sure. So the working relationship with the research team is actually kind of interesting. So in project year one, we had a little bit of difficulty kind of getting the project up and running until I was able to start talking directly with several of the main developers. I don't know if other ECSSers have had this experience, but sometimes it can be difficult if your only point of contact is the principal investigator. Getting information transmitted, from you through the PI to the person actually making the code changes is kind of like playing the telephone game. So it can be difficult to really make any significant headway. But this is a large project, so there's many people involved in this project. There's probably 10 to 15 different developers. I've been working for the last 2.5 years. I've been working with two in particular. One of Dan's students, Wentao Zhang, and a staff member at UIUC, John Larson. We've been working and copying Dan, of course, on all of our correspondence. But the way we've mostly done this is I will make recommendations through email or suggestions or things to look for, and they do the majority of the code changes because they know the code much more intimately than I do. There's a very large code. There's a lot of different pieces to it, and it would probably take me an entire year working just looking at the code to bring me completely up to speed on everything going on in it. But if we can provide feedback and suggestions to them, and then they can take that and translate that to the particular code and run with it, then that seems to be the way that it works best. So I tend to just offer suggestions. They go out and implement it, try it, come back to me with the results of those tests, and then we move on from there. So I think that's been the only way for a large code like that we can really get anything done.
Yeah, great, thanks. That makes a lot of sense. And congratulations on the CPU savings. That's really impressive. 12 to 14 million per year is it's really opening up a lot of opportunities for other researchers, as you say, especially in these competitive times. Any further questions for Luke? Okay, well, with that, I'd like to thank you very much for preparing the talk for us, Luke. And Suresh, if you could go ahead and grab the controls. Suresh is going to talk to us about the use of Apache Aravata in several ECSS science gateways. What we're starting to see is more and more requests from command line PIs to build gateways, and Suresh has been doing work with a lot of these PIs, some of which he's going to talk to us about today. So thank you very much, Suresh.
Yeah, thanks, Nancy. And you can see the slides and hear me okay?
Yep, looks great. If everybody else can mute also, that would be terrific. Thank you.
Great. And Nancy sent you the slides in case you cannot see. Hopefully you can use the slides as a reference, but actually you'll not need the slides much because I just want to make one simple point. I think thanks, Luke, for the great talk. I think that's kind of the example and the point of my summary. Quick overview talk is to give how can we build on those kind of efforts when Luke's and others, all the rest of the ECSS colleagues are working hard with these PIs, optimizing codes, porting them, improving the performance but significantly. How can we make them and make them broadly available to the community is the simple message of this talk. Again, I really enjoy these ECSS Symposium talks. We get to learn about how each of you are working with various projects and how we are starting out with the work plan, how we are working with the PI to further meet the goals and go beyond and keep renewing. Some projects get renewed for good reasons and so on. But I'm not going to go through that kind of a typical cycle, but actually walk through an overview of the ECSS projects. Mainly we've been doing here at IU by quite a few folks, Sudhakar, Ravinder, me, Marlon, and Lahiru, and Mary at various times. Various folks have worked on these projects. So I've picked some examples here, particularly to call out on how we picked up on or got added into the ECSS project, either during the work plan development stage or some of them later in the game, some almost towards the end, and then added a gateway component to the existing porting efforts or code optimizations effort. And how do we transition from that is kind of the examples I'll walk through. But the key goal, I guess, why we picked this topic instead of specifically talking to one particular project is we want to basically seek help from, you can consider this as a shameless pitch from us, to seek help from the rest of the ECSS on help with this goal on how can we bring more gateways, as Nancy briefly mentioned. How can we make these PIs who are starting to think go beyond this command line interfaces and make their codes and research available to larger community? How can we help them? Is what we need help from everyone, and hopefully these examples will provoke some thinkings on how to basically help the gateways community bridge, the gateway ECSS staff bridge with the PIs. So first example I'll walk through is the large eddy simulations turbulent flow project. This is a project from RPI, from the PI Mark Shepard, but mainly Cameron Smith. The research staff has been the main primary contact on ECSS project. I'll not get into the science details. First of all, that's not the point. But secondly, I'll also start exposing my ignorance on all these domains. So I'll try to not do that and be in my literate domain. But I think I believe we have David O'Neill on the call and Lee Hank probably too. So maybe they could answer the science questions and specific what the PIs are trying to do here. But the point here is on this project started out as a industry collaboration. David O'Neill was working with them, helping them bring their codes online on Stampede and yeah, I'm sorry if I'm not stating all the provenance correctly here, but we got added to this project when and the PI wanted to take these FASTA codes and now make it available like what they have worked on Stampede and build a FASTA gateway. So again, I've used the basic science description from the FASTA project for reference because like Nancy will be putting the slides online for reference, but I don't plan to walk through this and then we'll defer the questions to David and others, like if you have any on the particular what the project is doing. But the key point is, as an example, once the code got optimized on Stampede, like the group wanted to do larger simulations. So because here we see the gateways coming in different dimensions. For example, we have Terry Schwartz on the call. The Cypress gateway which Terry and Mark Miller and others work on, like have a large number of user base, like 15,000 and so on. FASTA gateway is an example of the other end of the spectrum, which is they only have a very handful of the user, but want to do large science. In this case, the attached figure, this figure is from a simulation they ran on Stampede, resulting from a 120-hour job. So naturally, so the gateway requests, like in this kind of cases, are like, and then like of course they wanted their users once the Cameron Smith worked with on the ECSS project with David and others and got the code supported. They wanted a web interface firstly, for their users like who are doing these large simulations, and then the second thing is, when this simulation goes for this long, they want auto scheduling features. So how can we? It's very as you know, and then the TAC folks can clarify here on the limits. But Stampede allows jobs to be submitted on the normal queue up to 48 hours. So if when a FASTA code wants to run a 120-hour job, how can can the gateway help them? The user will be requesting a large job, but they want the gateway to automatically split that job and submit multiple 48-hour jobs one after another, and then show the monitoring status of this kind of jobs. And of course, here the application checkpoints well at the end of the 48 hours when it stops, and when we resubmit again as a new job, it picks it up well. The code is very well checkpointed here. So here is an example of a gateway. We see totally instead of just broadening access, more enabling them to do more bigger things. And then the second request we see from the FASTA gateway is especially this is more to do with the graduate students and postdocs working with the PI's group and probably in their close collaborators. They want to compile their own versions of FASTA. They want to change something, and they have some variants. They want to keep using this. And how do we enable this? So these are typically not the typical gateway requests. The typical gateways, what we see is have a well-defined version of a code used repeatedly with different inputs and for different problem cases. Where when the FASTA group wanted to enable, how can we support these custom applications? So I'll talk some details on the gateway level details here. So this is achieved by describing what we call the gateway application abstractions. At the gateway level, we describe this is a FASTA application, and then here allow the power users to point to their own deployments. If they compile the code, in this case, they assume the typical gateway case, not every user has an account on the Exceed machine. They go through all to the community account. In this case, they probably these power users have their accounts or have access to the community account. They go build their own version and then point that back to the gateway and want to use their custom version of FASTA for their own runs. So and then and similar use case was they wanted to integrate their RPI campus cluster at RPI, but it has to you cannot directly SSH to it. It had to go through the one-time passwords and jump host. How do we enable that? Was part of the ECSS gateway request. So part of this, all of this have been done, and then also now Lee started to work with them on. They've just got a new XRAC, and then we started to work with them. I haven't seen the details on what they want to accomplish in the next ECSS project, but the gateway which was developed on the ECSS project, which ended in December, is deployed here again. Nancy, also to answer you, the reason this is not listed as production because the RPI group is trying to theme it. Right now, it has a barebone, probably a theme clone from Secret Gateway. They're trying to customize and make it look like the FASTA gateway and RPI centric gateway. So hopefully they will finish that user customization and then more tune it for their engineering users, and then come back and make the gateway production so that everyone can see it from the public listing. So again, switching on to a different project here. I guess like Mark and Sudhakar are on the calls. Again, I'll defer to them on the details. Like here is another example gateway, the vortex shredding simulation gateway, on how do you run NEC 5000 applications on Comet. So in this case, yeah, there's a demo online. Like feel free to, when you have the slides, look around. Here, Sudhakar, can anyone create an account if you're not muted and then play with it, or is there an approval process?
No, there is no approval. Anybody can create an account.
Okay. Yeah. Thanks, Sudhakar. So, Sudhakar, while you're on it, so do you want to discuss anything challenging here, especially because you've been working on their big, large data sets and so on? What they bring to the table here?
I mean, there are no particular challenges. I mean, it is mainly for educational purpose initially. So the target is to actually reach out to even Arne Polstein says even young scientists like kindergartners all the way to graduate students on this one. So there are two different kinds of flavors that need to be provided. One for children to get excited about these flows, just the visualization of it, and then maybe ask some questions to just for their interest. And for undergrad students and higher level, for these people there are more details about some could be homework problems, and they need to get a lot more details as to the actual computation itself. So I mean, apart from that, I mean they're still building the portal. The number and types of parameters used is still, I think, in the flux at this point. So they're a separate testing gateway. I think it's called vortex shredding alpha. If you add alpha, you get another one that they're using to test some new ideas and new presentation. So this is still evolving. So it's
yeah. Thanks, Sudhakar. So here's this is another fine example of how it started as a code porting efforts, and then how to help the PI group first of all run the application, and then once as Luke was referring to, once you get those kind of gains, how can we make sure that the larger community who was using the same application, how can we maximize on these gains, by enabling them to run through that particular optimized code through the gateway is a good reference I want to point to here. And then in this case, many times, like in the case of FASTA gateway or NECFire, like the vortex shredding gateway, we'll see that from the Exceed standpoint, we help them on how to plumb and work with Exceed more efficiently, but there are more than larger efforts. In this case, Sudhakar is interested to help them, and he's been working with Emery Brooks on using a framework called GenApp on how to provide some custom apply, because there are two challenges, especially for these kind of applications. One is how to efficiently make them work on Exceed and connect them through programmatic interfaces, and second, how to help the user communities, especially as Sudhakar is describing, when you're going back to kindergarten students, how to help them make and create these input files, help them validate those input files in a nice, friendlier fashion. So that's typically, many times it's out of the context of Exceed, but the ECSS, the gateway staffers try to find other interesting things, and then they continue to work on them, and so on. Moving on, again, I'll come back to some more examples, but I want to quickly point other couple of examples. Especially there are new the new paradigm of Exceed machines coming in with Jetstream at IU, and So as an example, like many a times we see these ECSS projects, like a lot of them say request accounts on allocation on these newer machines. They want to try it out. Mostly they are startup allocations. How can we use them? And here's an example like where we try to bridge from a gateway, try to demonstrate how they can use this VM-based environment, maybe to, in this case, this was done for the supercomputing demo, but how to use this cloud infrastructure to deploy. In this case, it's a weather simulation, like it's a climate simulation. You're running through a data viewer called integrated data viewer from Unidata group at UCAR. So how can you make that? How can you spin up a VM on demand and then run this computation and visualize these data sets? And let's say if the faculty is teaching a class and then they request lots of Jetstream VMs, they can have each student have their own VM for a particular amount of time, work with it, do all the interactive visualization and run computations and bring them down after the class and so on. So similar to Jetstream, we already have been working with a PI, Nausheen Ghaffari from Texas A&M University. So this is waiting for the bridges to come online. Hopefully we learn new things and we can bring them back to other projects. So Nausheen and group were using as part of the ECSS project. This is an ongoing project which ends in end of March. So they were using, they started on Blacklight and then briefly ported to Greenfield, but mainly waiting for the bridges to go online. It's kind of hibernating right now, while the mission is coming online. But what we hope is what we learn from these ECSS projects as the code porting goes on, and what we can work with them on the gateway aspects, and then anything we learn here, which will be broadly applicable to the future projects. Again, I switch gears here and then put, pardon me if you see this as a sales speech, but what the point here, what I'm trying want to bring out is whenever we start on these ECSS gateway projects, this typically building a gateway or especially sustaining it after the ECSS ends is a very hard problem. Here we try to leverage a lot from NSF grants, we are involved, which is outside the context of Exceed, but it's an NSF cyber infrastructure funded grant. In this case, when we start the project, we take an out of the box, like the FASTA case, take the out of the box features what we get from the Apache Airavata, like what other gateways like Ultrascan, which I'll point some more details towards the end. How can we take that and then apply to FASTA? And then now the FASTA group make this special ECSS request that, okay, please support auto scheduling on Stampede, up to 120 hours or more, just in the multiples of the maximum wall time. So when we make that contributions, we contribute that back after the during the ECSS project or outside or after it. We try to make this contribution back into these Apache frameworks. So this is the core thing of what, especially what we've learned a lot in the Apache Software Foundation. Open source is not just about putting what we write, the source open, but open source is really about the open community, giving the contributions back and giving the criticism back. As Mark Miller from the Cypress Gateway says, when a user complains something is not working, it's a blessing. So how many blessings you get is, well, robust, this or as a service or a software in these cases. So how many contributions, each one we can get, maybe sometimes it will be bug reports, it's not working. Sometimes they're actually new feature additions. So we've been able to, on a short time frame, work on these ECSS gateway projects by working in this ecosystem and then going through this, repeating and rinsing this cycle. So again, I'll leave the slides for it. I want to leave a lot of time for discussion, so I'll skip over the actual details about how Airavata is, or the technicals on what's actually happening and building these gateways. You can look at these slides and later always feel free to contact us. But in a nutshell, it has a it's a big middleware. It's a middleware which has support for all the computing machines. In this case, Exceed plus some of the non-Exceed examples I'll walk through. And then how do you run those services at scale and in a secure way, working with, for example, in a security audited way, with how do you store different community account credentials, how do you renew them, manage them, and the faster example I was trying to say, how do you provide the application abstractions so that you can quickly bring in different versions or in different deployments together. And then in the idea with an out of the box, like what's provided is as a reference API implementation implemented in PHP. The reason we choose PHP was most of the target science groups, like we want, for example, a physics grad student to take it and plagiarize it and customize it for their own need and extend it and so on. But there's an API. It uses a technology called Apache Thrift, which is primarily championed by Facebook for their multi-language clients. So how can we take this and develop a gateway interface or a command line clients in various programming languages? So and then how to make it easy for the administrator to administer such gateways? The administrators, it's a two-way game. Like when we go to the PIs and try to convince them to build gateways, the first question they ask is, how should I operate this? I don't have resources. Or I'm busy with my own research. I'm happy to give out whatever I'm doing, but I'm not going to operate. So in the end, there is no good answer to that. Ultimately, someone from the PI group has to commit to operating it and write allocation proposals on behalf of their user community. But what we can do from the framework standpoint is make it easy so that they just go to a one simple dashboard and watch what's happening on a gateway and then act on failures, submit exceed help desk tickets when some things go wrong, or contact the middleware developers, in this case, the IU group here. We're running services and so on. So how can we make that? And then we support this through the partly in our group here is funded from the ECSS, and also the rest of it comes from this NSF funded SciGap project. The key thing here is the SciGap project has really helped us as an exit strategy for the ECSS projects. Previously, before SciGap and early years of Exceed and Terragrade, how to exit out of a gateway ECSS project is a very tough problem, because once we develop it, when we try to pull out of the ECSS consultant, the gateway APIs almost keeps coming back. Oh, if the consultant goes away, I cannot run this gateway. I don't have the expertise and so on. So the key thing, the key mission of SciGap is how can we help the gateways scale operationally? Because typically if it takes a half an FTE to an FTE to operate a gateway and keep maintaining it, how can we make 1 or 2 FTE support a few dozens of gateways? So to do that, really need to get into the details. I'll skip for this context. Maybe we'll have a detailed talk on the gateway community forum in the future call. But how can we make these services self-reliant? How can we make them auto-scaling? How can we failure resistant? How can they make sure they come up? The infrastructure itself is robust. At the same time, how can they work when an Exceed commit goes offline? Immediately alert the PIs or stop the gateway jobs and only release them back when the file system is back, is healthy, and so on. How can we help more and more the ecosystem more improve? Because we are trying to talk about layers of best effort infrastructure here. In this case, it's just not about fault tolerance of the software, the gateway you build, but how well you can tolerate the failures upstream and downstream. How to incorporate all of that is the key thing from this the NSF-funded SciGap project. But from the ECSS context, what it helps is, for example, last veteran project I'll go through, it's used, this is a project in South Korea, uses, they take the software and build it and incorporate it, they run their computations on Amazon, and then the local clusters and in South Korea, and then they contribute that back. And when we get that back, how can we take those contributions and help a gateway working from Exceed, who always come with these requests? I have a campus cluster, I have a local cluster, I want to integrate that as well as federate to Exceed, like the spillover jobs and so on. So helping, working with other projects beyond Exceed too, and then making all those contributions back into the frameworks really helps. And the last example I want to say here is the AlphaScan Science Gateway. I'll skip the details. Like, you probably heard about this in the previous ECSS Symposium talks too. But the key thing here is we see the unique challenges Ultrascan, the science gateways brings is the gateway is really federated across the world, not just the user community, but the gateway is in this case. There is a laboratory information system. The gateway is acted off. Each instrument has typically a gateway. So there are about like 70. Roughly 70 odd cluster of small micro gateways you can imagine, and then these gateways are in US, in Germany, in India, in Australia, all trying to work with their local resources and with Exceed, and then like some clusters in the PI's group, the one with the PI's group managers. How can we manage and help them? So when projects like Ultrascan are using this common framework, this has been a very educational for us, like how we learn from each of these projects and then contribute this back. At the same time, how quickly we can take this software used by a prominent gateway and apply to a gateway which is building up from scratch and sustain it with minimal cost and so on. So I'll stop here, but if any of this is interesting, please, if you're not already in, I'd highly encourage you to subscribe to the Gateway mailing list, where Marlon conducts this bi-weekly symposium where you hear some of these kind of details from other gateways coming and sharing their success stories. Again, I stop with a request again saying that the point is to show that we really need help, we need help in bringing up these new gateways. We want to go out and work with the PIs on a quick, short time span, help them, the optimized codes, really made it available for a larger community, and learn more new things in these things. With that, I'll stop here and ready to take questions.
Suresh, thank you very much for a very interesting talk. Let me open it up to folks on the phone line and on the webinar. Do we have any questions from anyone on the call for Suresh? That was a lot of information in a short time.
This is Ralph. I found this extremely impressive. I have a question about what I thought you were saying about FASTA. Is it the case that you created a gateway and somebody who has a different algorithm for doing something which is buried deep in FASTA can adapt that gateway so that it runs their algorithm instead of the one that FASTA uses?
Almost like that, but mostly in this case, instead of a new algorithm, I think, Ralph, I particularly don't know the details what exactly they're changing in the FASTA. There is a little bit of that too. They're trying a different algorithm, but more and more, what I hear from them is the graduate students who are researching, who are staying fine-tuning the algorithms, and then they need to recompile the code and try to use it. And these graduate students don't necessarily understand how to work with Exceed. So, but they compile the code. They're not used to running these long simulations, and then come back to the gateway and use the gateway to run. So there's a little bit of what you're saying, right? They're trying various of the algorithms or trying new algorithms.
So, but is it the case that they can do this without your intervention? I mean, without the intervention of the ECSS Gateway group?
That's the whole idea, Ralph. We try to want them to make them self-sufficient and make them, once it's deployed, we need to first show them how once they recompile, how they come back to the gateway and reconfigure it to point to the new algorithm. That's about it. Once we do that brief training, we are not involved. They do it without us getting involved.
All right. That is terrific. Okay, thank you.
Ralph, this is Sudhakar. For some of these computations, including the NEC 5000, the users do submit what's called a user subroutine, which is actually used to recompile the code on the fly and generate a new executable, which is used in the execution and provide results at the end of the simulation. So that is already part of some of these gateways. I mean, not only for NEC 5000, I think even for Abacus, I think they can submit, user-derived function that can be embedded, and a new executable is created on the fly. So these things are actually possible right away. And what Suresh was saying about actually getting a new executable that is compiled outside that is integrated into a gateway will also be possible in the future.
Yeah, that's the case for NSG portal.
For which one?
The neuroscience gateway.
Uh-huh.
We allow users to submit their own code to be compiled and run, but we vet our users. We know who each of them is and that they are a real person.
Okay. Very, very impressive.
And I see that we're a couple of minutes over time. Any other questions for Suresh? And the slides from both presentations should be up on the symposium website later on today, as well as the video. Okay, thank you very much. I want to especially thank our speakers for preparing such very good talks for us today, and thanks to all of you for your patience with all the web conferencing confusion. I promise we'll have it straightened out next month. So hope to have all of you back for the February symposium. Thanks again.
Thanks, Nancy.
Bye.